you forget. All right. So, hey, there's Pivnert right there. PV equals nRT. Now, we'll be fine. Don't write it down yet. So, well, whatever. So the macroscopic properties of an ideal gas are related to the ideal gas law, PV equals nRT. This is called the ideal gas law. Like all of you, eventually, you're just going to enjoy life and have the ideal family, but in reality, no one does, right? We all have some problems. I won't go into details. But like gas laws, we call it the ideal gas law because it's like if every single thing was perfect, we would do this. We ready? Yes. Okay.
Thanks, dude.
Yep. Thank you. All right. Enjoy. Thank you. 2 summers ago, I got cement, and Jesse, I ordered 4 yards, and he was like, "Can I just tag along with yours and I'll pay half the shipping or what the delivery fee or whatever?" I'm like, "Sure." So he calls the cement company, and he's like, "Yeah, I need to add an extra yard." They're like, "All right, what order?" He's like, "Tom Davidson's." And we're like, "Okay." They didn't ask for anything, not a single thing. So if you know anyone getting cement and you want some, just call them up. They don't ask for any identification. All right. Anyway, moving on. It's really expensive. My heavens. Yeah, and it's just like rocks and dirt. But anyway, moving on. We'll get this later, but this is our focus today. Are we actually ready to learn stuff? Good. Well, it's too late. We're not going to start with problems. Don't worry. All right. Now, I wouldn't write a ton of notes. I always say that. And they're like, I should have taken notes. It's up to you. But I'm not going to stay here long enough for you to write every one of this. So this whole chapter is about gases. Now, sometimes it'll be a reaction where a gas is formed. So it'll seem like that doesn't sound like a gas, but whatever, trust me. So unlike liquids and solids, gases expand to fill their containers. If I remember right, that's like a multiple choice question on this test. You have to know that some weird thing about it is it fills its container. Because if I turn this on, and it like, if I plugged it, the water wouldn't just dissipate throughout the whole room, right? It would just stay there. Gravity would pull it down and stick there. All right. This lab book is not expanding to fill this room. It's just here. But every time I exhale, my carbon dioxide and other stuff's going into the air in this room, and it will spread out to fill this room. Okay. They expand. They are very compressible. A solid and a liquid are not compressible really at all. All right. This is my picture of hydraulics. Hydraulics work by trying to compress a liquid, and it won't compress. So what they do, they apply a pressure to a liquid over a large area, and then they have it reduced to a small area. What? No, what?
Yeah, it does work. But it works.
The what? No, you don't calculate this. It's really hard. This is just the theory.
Don't worry about it.
All right. So the small pressure applied over a large area turns into a huge pressure over a small area. Is that good enough, Tim? Okay, we're done with hydraulics. Too much PTSD. I apologize. Moving on. Ignore everything I just said. All right. Gases have really low densities. What color did you order for yourself?
It's under Peter's boy toy.
Okay. That won't look weird at all at the hotel. Hi, I'm checking. I need to check in. My name is Peter's boy toy. Oh my gosh. I'm blushing. All right, they have low densities. You need to know just the basic properties of a gas. They're pretty easy. Okay, we're going to talk about pressure. Pressure is not super hard. All of you are under pressure right now. Pressure is the amount of force applied to an area. That's all. It's not the hardest thing ever. So like if I push against my head with my thumb, it doesn't feel great, but I'm fine. But if I take this pencil and push it as hard as I can against my head, it hurts a lot because there's higher pressure because there's less surface area, right? I would never shove a pencil through my head. I'm sorry. Kind of graphic. All right, now you are under pressure. You feel it when you drive to Manaway or up to Logan. You feel it in your ears, right? Like, oh, I didn't feel good at all. All right, it's poor people that live up there. Okay, pressure is force divided by area. The pressure you feel is this giant column of air over you constantly, just keeping you down. Now, the pressure you feel is the atmosphere on top of you. So conveniently, we call this pressure 1 ATM. Yep, or 1 atmospheres. So now we are around 40, whatever, 100 feet above sea level, like 41, 42, I can't remember, 40, whatever, doesn't matter. So we are a little under 1 atmosphere, but like in the atmosphere is really, really tall. So yes, we're a little under 1 ATM. It's like 0.989 or something like that, but it's not a huge change. So anytime in this class, unless I tell you otherwise, the pressure is 1 ATM. And it's really pretty easy. Okay. Okay. We don't use pascals in this class. We don't use bar, but if you take like, I think the airplane class or aviation, they use bar, which is 105 pascals or whatever, 100 kilopascal. Anyway, whatever. You don't care, right? We don't care. We're not to where we care yet. Okay. Millimeters of mercury or torr. This is old, but we kind of use this a little bit. If you watch TV and watch the weather, they'll be like, the barometer today is at 29.89 or something like that. And that would be in inches of mercury. And we don't use inches. So we use millimeters of mercury, which is literally, it's kind of dumb and old, but they take a bowl of mercury, they put this vacuum tube inside of it, and the atmospheric pressure pushes the mercury up, and they measure how high it is, and that will tell you the amount of air pressure, the barometric pressure, the pressure of the atmosphere. Okay, and the weather is extremely dependent on this. I love the weather. I could teach that for a couple of days. But high pressure, I just can't not, okay, it has nothing to do with AP chemistry. High pressure means that the force of the atmosphere is stopping things from rising. And weather-wise, we only really care about one thing rising. A high pressure inhibits rising water. And if water can't rise, water doesn't go up, it doesn't cool, it doesn't form clouds, and it doesn't form weather systems. So right now, we're probably under a changing pressure, but it's higher than it was a few days ago. For 5 consecutive days, we were under a low pressure. What's the data now that I've said this, that you know we were under low pressure? It was stormy. A huge low pressure off the West Coast. That snowed 170 inches in 5 days in the Sierra Nevadas. That's a lot. No, that was higher than that. That might be right. I can't remember, but it was 17.5 feet, whatever that math is. Okay. Now, so low pressure, that means water can rise. That means clouds form, storms form. That was hard for me to say. Anyway, moving on. You don't care. What you should care about is this right here. This is a conversion that you'll be asked to use a lot. In this class, we're going to use ATM 99.9% of the time. But some problems will give you the pressure in a unit called torr, which is millimeters of mercury. And the ratio is that there is 1 ATM for every 760 torr, or vice versa. In a problem, if you're given torr, you must always divide by 760. That will put it in ATM. The reason we want it in ATM is because PIV NERT has an R in it, which is a constant, and that constant will be given to you where it has ATM as part of it. It's kind of confusing, but just remember, given torr, take that number and divide it by 760, and that will give you ATM every time. 760, I will say no, you don't have to memorize that, just like you didn't have to memorize your name. You used it so much that it's not memory, it's just automatic recall. And you're like, that's the same thing, shut up. Okay, moving on. Okay, we don't care about that. Standard pressure, that I kind of already said, it's just 1 ATM or 760 torr. Okay, that is at sea level, so technically we are a little bit under. So like again, 0.98, 0.991 or something like that. It's really close to 1. Yep, unless it gives you a different number. Okay, now we're going to take Boyles Law here. We're going to take 3 laws and we're going to talk about them individually. AP thinks this is important. I think it's important because my mom's maiden name's Boyle, so duh. And anyway, my mom will still, like, it's been 80 years removed, and she'll be like, oh, that's the Boyle in you. I'm like, no. There isn't any. Okay. Boyle says the volume of a fixed quantity of gas, fixed quantity just means that the amount of it doesn't change, at constant temperature is inversely proportional to the pressure. Okay. So let me put this maybe in some English that makes sense. If you squeeze a balloon, it gets smaller. Okay, the volume of the balloon would get smaller if we could just squeeze it universally, right? Oh boy. Now the pressure is going to go up. So we have a relationship here between the volume of a gas and its pressure. The higher the pressure, that's the arrow, the smaller the volume, or vice versa. How would you describe this relationship here? Inverse. So volume and pressure are inversely related. In math, that means that volume would be on top and pressure on the bottom, or pressure on top and volume on the bottom. Are we okay with that? Okay, next up. Whatever. So don't write much of this. But as P of E are inversely proportional, plot of E versus P results in a curve. Don't really worry about that. Yada, yada, yada. This means a plot of V versus 1 over P would be a straight line. You don't need to do that. Don't even write it. I refuse to let you write that down. Okay, next is Charles. That's ironic because my grandpa's name is Charles. Basically, my family invented this stuff. All right, the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature. So don't really stress about the word absolute. We'll just say it's temperature. So what we're saying here is that if I heat a balloon or increase its temperature, the volume or pressure increases. So the volume is, and it's not equal, but it's roughly proportional to the temperature. If the temperature of your balloon rises, the balloon expands. And you've seen this probably as a kid when you cried because your car, or you had your balloons in the summer in your car and they popped. That's because the temperature went high, the volume expanded, the pressure expanded until it couldn't hold them anymore and they popped. You okay with that? Or vice versa, we could cool the balloon and it gets smaller and doesn't float anymore. Okay, so this would be what type of relationship? Directly related. You with me so far? And that graph would look like just rise, a positive rise over your run versus the other one, which was a negative rise over your run. Okay, then Avogadro I am not related to anyone named Avogadro that I am aware of. Yeah, this is definitely Avogadro. He's the guy that came up with the concept of moles, really. He says the volume of a gas at constant temperature and pressure, so we can't change the temperature or the pressure, is directly proportional to the number of moles of the gas.
So how much gas we have determines how big it is.
Yep. Yep. It's almost like if you blow more air into the balloon, it expands. I don't know. Kind of think that's reasonable. Okay with that so far? Mathematically, this means volume is roughly proportional to the amount of stuff. And the amount of stuff in chemistry is moles. And we're going to use moles equal to N. That's supposed to really not be uppercase. So N just means number of moles. So we now know that the volume is roughly proportional to the amount of moles. And that means we have up here. Who's with me so far? Okay, so here we go. I know that volume, I just learned, is roughly proportional to the amount of moles, right? And if I were to draw that graph, as one got bigger, one would get bigger, and it'd be roughly like that. Fair enough? I learned that volume was, I keep doing that, roughly proportional to temperature, right? That the higher the temperature, the higher the volume. And if one goes up and the other goes up, it would look like this, right? But then we learned volume was roughly proportional to 1 over pressure, which is just an indirect relationship. P means pressure. And so that graph would look something like this, right? Everyone with me? All right. So I can actually use what's on the screen to come up with an equation that relates volume to moles, temperature, and pressure. The arrows show me where the variables go. So I'm going to say volume is roughly proportional to what ones are on top? N and T, but inversely proportional to pressure. The arrows show where the variables go. You with me so far? Okay. Now, in science, a lot of times, like we know there's relationships, but they don't work out perfect, especially with units. So in order to make these roughly proportional to, scientists have come up with what we call the gas constant. It makes these turn into equal signs, and it is represented with the letter R. And I do not know where R goes, or where it comes from. I mean, I do know where it goes, and it goes right here. So just based on the 3 relationships and then trying to get them to talk to each other, that's what R is. We now have this relationship where volume is equal to N. I'm going to put R in the middle because it's usually written that way. T over P. And this is oftentimes referred to as PIV NERT. It's the same exact equation. It shows the relationship between pressure, volume, moles, and temperature, and then this constant that makes everything talk to each other. That's a great question. the constant is equal to 0.0821 moles liter Kelvin or something like that. I can't remember the unit. Oh my gosh. I was so comfortable right there. Look at that. All three of them. All right, don't tell me it was for the dentist. Okay. Do you even go to the office for a dentist appointment? Or did you just like, all right, girls? Yeah. At dinner every night? It's like, let's see. All right, are we okay with where this equation came from? It's not the worst thing we've done so far. Okay, so this equation, it's given to you on the AP test. So you don't have to have it memorized, but you will. Like close your eyes right now, say PIV NERT, and then tell your partner what the equation is. PIV NERT, PV equals nRT. Piece of cake. Okay. So here, this talks about R for a minute, and then we're just going to do math the rest of the day. So the constant of proportionality known as R. Now, I'm going to capitalize it half the time and not half the time. It doesn't matter at all. It doesn't matter at all. I don't know. Should, maybe it's a capital R, but it doesn't matter. All right. It's the gas constant. And we, there it is, liter ATM per mole Kelvin. That's its unit right there. This is the one we will use like at least 99.9% of the time. And we'll use this one in chapter 19. So like, don't even worry about any of them except for 0.08206. Did I say 21? Okay, it's fine. You'll see it both. 0.0821 is just rounded. And that's, I think they give you 0.0821 on the AP test because it gives you the constants. Either one will be fine for all that we're doing. You okay with that? All right. This one relates energy and PIV NERT. It's really different. And this one you can memorize later. It is 8 pi, as I call it. And you're like, what? But it'll make sense later. But for now, don't worry about any of them except for 0.0821. And that's the one I will use. It's just rounded. Okay. And it's what makes all the units come together so we can get a clean answer. All right. This is from one of the AP videos. This is not math yet. This is just thinking and applying PV equals nRT. It says a gas in a rigid container. You're going to see the word rigid container. I guess that's 2 words a lot. And if you look right here, what it means, a rigid container means the volume is fixed. Okay. Everyone, you have to know that. A rigid container means the volume doesn't change. Go ahead. Pretty much everything that isn't a balloon. Okay. So in question number 1, we are not changing the volume for sure. The container develops a leak, doesn't sound very rigid to me, but whatever, which is stopped when the pressure becomes 2 atm. So the question is, what does that do to everything else? You don't need to worry about R right now because it's a constant, right? So think about what has changed in number 1 with reference to PV, N, and T. Will you read that one more time and talk with your partner and see what you think of what has changed overall? All right. Let's talk. We ready? So the pressure obviously went down, right? Because it told me it did. Next, what happens to the volume? It stays the same because it's in what? A rigid container. Now, I heard these guys talking, well, the volume expands because it left. That's true, but we're talking about the stuff that's in the container. So if it's a rigid container, the volume is always constant. What happened to N, the amount of stuff? It dropped how much? Half. All right, because the pressure went down half, but nothing else really changed. So it doesn't say the temperature stays constant, but is there heat or anything added or taken away? No. So the temperature stays the same. So the pressure went down ultimately because N went down. You okay with that? The amount of stuff, it's half, then it's half. Okay. Number two, a balloon is filled with warm air and is taken outside on a particularly cold winter day. We could do that today. The student notices that the volume of the balloon has decreased by 1/10 of its original value. Okay, well, what happened to everything else? Talk with your partner. How was your trip? You look tan. All right, here we go. So we know the volume has decreased. We know that because it told us, right? Correct? All right, so what happened? Whoops, I guess whatever. I'll put it right here. What was the main thing that changed? Like what caused the change, I should say? The temperature. The temperature went down, which means the volume went down as well. And what do we think about the pressure? It goes down a little bit too. It's probably around similar, but it would go down a little bit too. N would do what? The same. Nothing leaked out or was added. Okay, number three, a gas in a movable piston. All right, you'll see this a lot and it's really dumb. I think I've drawn it once before. A movable piston system, you just have a tube and then you have the piston, which can go down or up. Okay, so that's how your cars work. All right, a gasoline car. There's some electric nowadays. So here we go. With an initial volume of 20 is compressed. Okay, so it was 20, whoops. But then we compress it, oh boy, down to 5. Something's going to happen for sure. All right. Half of the gas molecules are allowed to escape during this process. What? That's kind of dumb. Well, half of the molecules. So that part, I can't answer the 20 or the 5 because they're not the same thing. Okay, take a minute and think about what happens here. You don't know? Okay, what do we think? So N's gone down because it told me it did, right? So N goes down, V goes down because it told me it did, right? What do you think happens to the pressure? The pressure goes up. Anyone have a number for the amount of pressure going up? It doubles. It should go up 4 times, but half the molecules, so you divide 4 in half. You all right with that? And on these reasoning ones, you don't have to give exact math. It's just general. And then the temperature most likely it increases typically. All right. Why? Because temperature is measured, it's kind of weird, by the force at which these things collide with the wall. So if you make the walls a lot closer, they're going to hit a lot more often, and that will increase the pressure at which they hit the walls, and that's roughly determines it. The temperature is related to that. Okay.
Because like they bounce around.
There you go. Okay, now that was fun and all, but let's do math. I love math too. Here we go. This is a really similar or really typical problem in Pivner land. 10 grams of CO2. That's a red flag right there. Aren't we learning about gases? All right. We need moles, but this is giving me grams. It's not hard. How do you convert a gram to a mole? Divide by its molar mass. So 10 grams divided by 44 grams is 44, isn't it? 32 plus 12. Okay, everyone look at your partner and say, I know where you got 44, or say, I don't. Okay. Everyone know where 44 came from? Good. It was C, which is 12 plus 2 times 16. That was O. That's 32 plus 12, 44. Okay. 10 44ths is easy. That's 5/22, which is roughly 0.28. But 228. Oh boy, that's highlighter tool. That looks hideous. Okay, so you said 0.228? And I'm going to just write moles CO2. You okay with that? Why do I need moles? Tell your partner. Okay, what letter is the moles representing? N. N must be moles every single time. N must be moles every single time. Okay, here we go. So I'm just going to say 0.227 moles of CO2 are in a 3-liter rigid container. What is the pressure at 355 K? Okay, our temperature must be in Kelvin also. How do we go Celsius to Kelvin? Celsius plus 273 equals Kelvin. Now it's already given to me in Kelvin, so I don't have to worry. So I would have had memorized PV equals nRT, and then I don't know, with algebra. So if I need just pressure, I take V underneath. Are we all right with that? So pressure is equal to nRT divided by volume. So then just plug it in. 0.227 times, there's not enough room. I'm going to go down here. 0.227, that's your N. R is 0.0821. And then T, it gave me 355. And my volume was 3. And I just type it in. What'd you get? 2.205. Who agrees? Okay. What would the unit of this be? ATM. So this would be under roughly twice as much pressure as we are sitting right here. Thumbs up if you could do that. Okay. What? There's not a lot of curveballs. Sorry. Well, there's definitely that. But the good news is you don't have to do the math when it isn't this way. Uh-oh. I had like 5 people say they had that number. Did you get 0.277?
Are you doing it by all the decimal there?
Yeah. Okay. Ready for number next? Okay, what volume? So hold on. We should memorize PV equals nRT. So what should it should be rewritten how now? V equals nRT over P. Okay, what volume of gas will be produced when 25 grams of sodium carbonate reacts with 200 milliliters of 3 molar HCl? You've got to be kidding me. No, I'm not. Welcome back to hell. This is a limiting reactant problem. Yes. Hey, let's do an easier one first. Sorry, I'll go back. I'll just make one up. Nope. We are right on track. We are right where I want to be. We're a tiny bit. I usually give you like reading assignments over the break for this chapter, which I didn't because we did so much the last 2 weeks. So, I mean, we're behind on the reading assignment, but we're not really behind because like 2 of you would have done it anyway. Yeah. Okay. Okay. I didn't feel like writing the whole sentence, but what would the volume of gas be under these conditions? You have 28 degrees Celsius. That's a red flag. That must be converted to Kelvin. You have a pressure of 1.8 atm, and you have an N of 1.05 moles. See if you can find the volume. Plus 273. All right. Don't pick on Isaac. That's the student government's job. They bully him like crazy. Okay, when you have an answer, check with your partner, see if you have the same number on your calculators. But you know, but some people aren't. Meters? What are you talking about? The volume? That's what you're solving for. It's liters. Are we ready? What'd you get, Beal? 14.4? All in favor? Okay. Okay, 1 through 5 fingers. Given, without any chemistry involved, who can do the math? Oh, the Bensons. Kids these days. What? Yep. All right. Shh, please, you guys are talking. That means you think it's too easy. I want volume. I know that I've memorized by now PV equals nRT, which means V must be equal to nRT over P, correct? N was 1.05. R 0.0826, or sorry, 21. And temperature was this number plus 273. So 273.15 technically. Is that 301? And then I divide that by the pressure, which was 1.8. Good? Okay. We only have a minute, so we won't do it. But this is, please be quiet. We'll pick this up tomorrow, but you have to take 25 grams of Na2CO3, react it with HCl. You know, I'm sure that a carbonate reacting with an acid is a red flag. So I'm sure that you remember it makes NaCl aqueous, which I don't give a crap about because I'm doing gas laws, plus H2O and CO2 gas. Then you'd have to balance. Then you got to mollify it. Then you got to pivnert it. Actually, it's not that bad. It's not that bad. That means when an acid reacts with carbonate, it produces a gas.